So I'm going to talk about type theory for busy engineers. So normally, I give, at least lately, I feel like I'm giving talks about Rust roadmap and Rust features and things like that. And I decided to do something a little bit different. So yeah, who am I? Well, as I guess a legend, I was kind of going to make me feel a little blushy right now. But yeah, I work on the Rust type system and on the Rust language, and I've been doing that a long time. And one of the things I've noticed along the way is, at first when we were building out and designing aspects of Rust, we would do like little models. So we would say, okay, we want to think about how the type system should work. I'm going to figure out, just think about this part in isolation, and that can get you really, really far, right? And then we would think about a different part. And so we draft, make a model, a sort of some subset of Rust that's relevant, and just think about that part. But we've gotten to the point now where actually it's becoming kind of hard to keep the whole thing in your head, and we have unexpected interactions, or little problems that arise. And so I've gotten interested in how can we make a better model that will help us understand and extend Rust going forward and think about the new things that Rust should do, right? So the goal is to make something that lets you kind of play with the type system and experiment with it in prototype, not to build a shippable compiler, but to help you understand Rust as it is today and where it might go. And along the way, so that's what the goal of this project is, right? Mere formality. I was told I need to explain this for non-native Rust speakers. So there's an expression we say, oh, that's just a mere formality. Like it's a tiny little detail that you can get past. And in this case, mere is also the mid-level IR, the middle IR of the compiler. So that was the pun of this project. But the goal is to basically model in a formal-ish way how the type checker works, especially for the mid-level IR. So not really all the way to Rust surface syntax yet. But I'm not actually going to talk about mere formality here right now. What I'm going to talk about is a subset of it that I call formality core, mostly because formality was already taken on crates.io. I don't remember by whom. I should find them out. But but it's like a reusable part of it that you could use to model your own type systems if you were designing a language, like some people we saw today, like the really cool June language and so forth. Maybe it might be useful to them. I don't know. I found it fun for my own experiments. It's heavily inspired by a tool I used called PLT-Redx, which is in this other programming language called Racket. And it's basically the same thing. It's like a lightweight tool for playing with type system definitions and letting you kind of use the notation that you might have read in an academic paper and put it into your computer and run it and play with it. Now, I just said that you might have read in an academic paper, but what I've noticed is, shockingly, not that many people have actually read academic papers. They're kind of not designed for easy entry and understanding. And so what I thought I would do today is talk about how I think about it and how formality core, like use formality core and kind of to walk through a very simple type system and give you a feeling for what it looks like. And true fact, I have not done a dry run of this talk. I have no idea how long it's going to take. So either we're going to go way over or way under, and we'll take a bunch of questions. We're going to figure it out. It's going to be fun. But part of this is, I didn't really learn. I never really took a course on type systems, actually. I just kind of read things, and eventually it sort of made sense. So I'm going to be telling you kind of my way of thinking about it. Probably some people who've actually studied this kind of thing will have their own opinions. But right. So the way I think about formality core, anyway, is that I guess if you've written parallel systems before, like in Java, actually I'm going to tell you an anecdote because it's funny. One of the first courses that was taught in Rust was a systems programming course at Northeastern, and they went through and they taught the students Rust, and they got up to concurrency, and then they had a problem because they wanted to teach them about data races, but they couldn't produce them. So they said, okay, we're going to stop and we're going to teach you Java, and then you're going to learn Java. Now look at this horrible bug. Okay, let's go back to Rust. Now you don't have this bug. Okay, good. So Rust kind of made... That is a true story. But Rust made concurrency this thing, at least my experience of it, is, yeah, I can still have bugs, but it's kind of like I plug it together and I can think about it and experiment with it. And if it kind of works, it usually works all the way up. If it works for simple stuff, it works also for many complicated cases. Formality core has the same feeling. I want to bring that same feeling, but to experimenting with type systems. So here's the language we're going to walk through, called EG. And it does well, it's kind of a calculator, fancy calculator. So like this program, shockingly, prints 66 when you run it. I know. But it does some more stuff. You can have tuples, and they will be added up pairwise. You can define little functions, like so. And you can call them with this weird @ sign, which is because of a limitation I'll explain later. And you can even have generics. Right, so all of these are actually runnable examples in formality or in the program. And part of what I'm going to do today is kind of show you the actual program. Oh wait, someone earlier did this. I forget who. I think it was the first talk. Let's start with a cargo clean, just cause. So when you build something in this, it really is just a Rust program that you can work with. Let's see, source, or where did I put the tests? Under source, test, talk examples. Right, so like, for example, here's that first one. Hopefully you can read it. Executing 22 plus 44 gives me 66, and so on, right? Okay, so how do we define a programming language in a more formal way? Oh, what am I doing here? Oh, I'm just showing you that what I am not modeling in this definition is type inference. So you can have generics, but you do have to specify their values explicitly. That makes things a lot easier, actually. So how do we define a program more formally? It starts out with something called a grammar. How many of you have heard of grammars? Okay, good. I figured I wouldn't have to explain it too much. But basically that defines the syntax. Right, so you might write something like, oh, a program in EG is a series of function definitions, 0 or more, followed by some expression that's going to compute the value. Well, in formality core, we're going to define that, but we're going to do it with a Rust structure. So we might have, let's see what I have here. Yeah. So we might have this struct saying this is what a program is, and you can see it has fields, and you put an annotation on it called term. And that's a kind of bit of PL programming language jargon. A term is basically just a thing, something that you're a part of your program or a value or something we're going to talk about, essentially. We need a word for thing, so term is it. And in here, you put the grammar, right? So the $, that will tell you, oh, I'm going to parse the value of this field here in the input. And if you have a little star, that says take 0 or more things, collect them, and put them in a vector. Right? So this would be 0 or more function definitions. Of course, it's using traits and everything under the hood to drive the execution. And this would just parse a single expression. Okay, so that's a pretty simple grammar. Sometimes you have grammars that are a little more complicated, like the expression could be an integer, or it could be an identifier indicating a variable, or a bunch of expressions in a tuple. So when you have a choice of many different options, we'll model that with an enum. And we're going to say, okay, we're going to put the term annotation on the enum. And then for each of the variants, we're going to give the grammar. So these are the different choices. If it's an integer, it should just look like an integer. Okay. And when it's an anonymous field, I just call it V0, V1, and so on. So here, one little handy macro is this ID macro. That just declares a string, an identifier. So we're saying, okay, there's going to be an identifier type that I call ID, and I'm going to parse, if I see an identifier, that's a var. Okay. And here you see a little bit of handy notation. You can say $ with parentheses. That means a parenthesized list. So I've tried to put in like the common conventions you'll often find. And so we're going to parse one or more expressions and build a tuple. then we'll continue. Maybe we want to have plus, minus, times, and star. We can do that. That's just some more variance, nothing complicated. The only thing is I can add these precedence annotations to kind of guide the parser. So we're doing this declaration on our structs and basically telling formality core to generate, it's going to auto-generate a parser and everything else using these grammar annotations, right? One minor point is if you have recursive types, it's still Rust, they have to have arc, otherwise the type would have infinite size. That's no problem, and so on. And sometimes the grammars can be a little non-obvious, like let. So here we're declaring a local variable. It's going to be called ID or whatever. It's going to have an initial value. It's going to execute an expression. That's going to look like this, right? So I have the ID and the arc and so on. Okay, you get the idea. So let's look at an example. Now, we wanted to write some tests, right? Because the whole idea of this is you can write this grammar and then play with it. Let me see where I have some tests. Okay, here we go. So here's one where one of the things I can do is test my parser. So for example, I can take this, let me explain this now. So e.g. lang, I'll come to that in a second, but basically I have to declare my language somewhere. It just gives it a name and it makes a crate with a couple of boilerplate things. But one of the things it gives you is this function term, which will parse a string and give you back a data structure, right? So here I'm saying, parse me an expression from this thing. And so E is some expression, which then we can run a test. And actually we use the grammar to kind of help guide not just the parsing, but the debug impls and so on. So if, for example, we just write E : ? That's the normal debug impl, you get something that's generated with the grammar in mind, right? A kind of pretty printed version of it. But if you ask for the full detail with the hash sign, then you actually get, the standard thing you get from a debug impl. This is pretty useful when you're writing tests of the parsing because it gives you all the detail. And as some people who've played with my systems before will tell you, or when we didn't have this, it's kind of helpful when you're learning if you really want to know exactly what data structure you've got. In this case, in particular, we can see that the multiplication had higher precedence, right? We parsed x plus y times 3 plus 66. If we did that wrong, we might have, for example, parentheses like this. We might have a plus that was getting multiplied rather than an addition of a sum, but we don't. We have the multiplication inside and then the adds. Okay, cool. That's all just parsing, and it's not a particularly smart parser. Oh, I already showed you this. But you have to declare the language. Okay, this is boring. Well, one thing I'll note is you tell it what you want to have as keywords. But okay, boring. Let's talk about type checking. This is where it gets a little more interesting. So far we allowed you to define data structures and specify their grammar, and you kind of get for free a parser that will parse and give you what's called an abstract syntax tree, which is just an instance of those data structures, right? A way to view your program as a data structure and not as a string. But now we want to do type checking. And the type checking rules for this EG language are pretty simple. You can add, if you're adding things, they basically have to have the same type. So I can add 2 integers. I can add 2 tuples that are both 2 integers. But I can't add a tuple and an integer or 2 tuples of different arities. That should not work. So that gives us a question though, what are types in this language, right? The next thing we have to define, we defined what the program language is, but we didn't define the grammar of types. So the next thing you have to do is define that. We're gonna have it basically be, I'm starting with the simple, I'm excluding generics for the moment. It's an integer or it's a tuple of some set of other types, right? So that's just an enum with 2 variants. One is an integer, one is a tuple, okay? And now we're gonna get to this inference rule stuff. How many of you have seen something like this? Okay, how many of you understood what the hell is, what is going on here? Yeah, me either, yeah, okay. So, This notation is actually ridiculously simple. It's like the world's... How many of you have written in Tickle? Okay, oh, more than I thought. I have not written in Tickle, but what I do know about Tickle is that everything is a string. Well, this is kind of true here also, right? The way programming languages work, basically, or these rules work, it's like you took the world's simplest interpreter and you run it, and it has to be simple because we have to be able to map it to like mathematics. So it has to be very, very simple so that mapping is very, very simple so that we can formally prove things about it. But I'm going to kind of walk through it. The very first confusing thing about inference rules, in my opinion, is their name, which is like, what is that? What is inference? I don't know. I think of type inference. It's not really about that. It's about this English word infer, right? It's basically a rule that says, like, if I infer something, it means I figured it out based on something else, right? Well, an inference rule is basically how can we figure out a conclusion based on a set of premises if these things are true. In other words, you can kind of read them as, if you see a big rule that has a big line, the stuff on top of the line, that's the conditions. If X and Y, then Z, right? This is the conclusion. And then there's this thing over on the side, that's just the name. That's just so you can refer to it. So like here, these are the two conditions on top, and that's the conclusion. Okay. Sometimes there's no conditions, and then we just write a line. But it's a pretty handy notation, even though it's so simple. So here's an example of one of the inference rules you might write in EG, which is somewhat simpler. What is this saying, though? What is going on here? So we've got this kind of, even in this very simple example, we've kind of got this crazy notation. What's happening there, when you see a string like this is also a term. It basically has two different parts to it, right? Overall, this is basically a predicate. It's something that we can say is true or not true, or at least true or not known to be true. And inside of it, there are variables. So here, the t, that's a variable saying some type. I'm going to call it t. Oops. And actually, you could call them meta variables very properly, but let's just call them variables. Basically, when you have these letters, usually that's kind of the variable. So t is some type. Maybe it's U32, maybe it's parenthesis U32, U32. Gamma, by convention, I put it in here because I'm Greek, but I personally prefer to use the letter E because I actually speak English as a primary language. But gamma is usually used to mean the typing environment. It's basically the types of all the variables that have been declared, though it could have other stuff in it. In Rust, it might have lifetime relationships and so forth. It's kind of just a convention, right? So effectively, it's just a list of variable names and types for those variables. So we can actually define gamma, like everything else, when we're doing an informality, we have to kind of define this stuff with Rust data structures. So here I'm not using the term macro just because I never need to parse it. But the so-called environment is basically just a list of variables that are in scope and their type. And I'm just using a map. You know, it's a B-tree map actually, but goes from one to the other. I'm also carrying the program along with me. That's so I can look up function definitions when you call them. We won't use that right now. But so that's what we're going to call, when you see gamma, we're going to basically just think it means some environment, right? Okay. And this notation we saw, gamma parenthesis x, well, you could think of gamma like like a function you can call to get the type of a variable. So we'll do that by accessing the map. So what about the other stuff? We saw these variables. What about this weird thing? That's called a turnstile. Why? Because, you know, when you walk in the subway, the little thing turns. That's why. That's a turnstile, the thing that turns. And this colon, the answer is this is just stuff. It doesn't have any meaning. It's like opaque strings, like a name of a function. Effectively, the name of this predicate, if you want to, is like gamma colon. So it's kind of like Objective-C, if you did that, or Swift. I don't know how Swift works exactly, but in Objective-C, the name of a method is kind of strung out across, interspersed. So the name of this method, insert object, is actually, it's actually insert object at index, like one big string, even though you write it in parts. So here you could say the name of this rule is gamma colon, which is kind of hard to say out loud. Sounds awkward. So maybe we can give it a better name. We'll see, we will in a second. there are some conventions. So I said they're just random stuff. That's how I think of it. Like, you just have to accept it. It's just this is what they chose to use. But there are some common conventions people often use, like the turnstile separates assumptions, your environment, the things that you got from the outside, from the thing you're trying to prove with those assumptions. Like, if I know that the variable x is a U32, then I know that a reference to x has type U32. That's based on this assumption. And colon usually means has type. Okay. So you could kind of read this as assuming gamma, then E has the type T. And what I would say is this was actually like a turning point for me, personally. When I realized that this weird symbol basically meant assuming, or lets me say, that's how I thought of it at first, I remember. Lets us say, like this lets us say that. But I was like, oh, I can read this now. It reads like English instead of this weird string of symbols. So just knowing what people mean by it is usually very impactful, I would say. But how will we write that in formality? We're just going to write it like a Rust function. So we have to give it a name. I'm going to call it type expression because it computes the type for an expression, like the type of an expression. And then we're going to put, for each of the variables, they're going to show up as variables, right? But you'll notice that some of them, the first two, show up as parameters to this function, and the last one, the type that comes after the colon, that's actually the return value. So that's a bit of a less abstract. Normally, when you define the rules, there's not really a notion of input and output. It's just like a relationship between these things. Like, if you have this variable, it has that type, and you can kind of run it in both ways. But when we're really going to execute it in real life, we have to think about what's the input and what gets computed from the input. Otherwise, it's not like a function, executable function. So usually, so I just kind of bake that in, right? And so what this is saying is, given an environment and an expression, we should be able to figure out what the type of that expression is. And that's actually a property, right? We're not going to like guess it. We're going to have to, it has to be something deterministic. But okay, so here's how we're actually going to write it. We're going to write judgment function. And what this is it's a crazy wicked macro that I'm going to show you later. And then we're going to start with what looks like a fairly normal Rust function, except for this part here, where I have 2 arrows instead of 1 arrow. And that's because what we're going to do when you write this typing, it's possible that actually that we're going to write a series of rules that we can use, like the rule we saw. And it's possible that more than one of them applies, right? It's also possible that 0 apply. So in some sense, we're computing all the possible types for this expression. And if there are no possible types, then it's not a well-typed expression. It's invalid. But if there's more than one, no, that might be okay. Sometimes there's many ways to draw a conclusion. Any one of them is valid. Sort of like A or B, right? It's true if A is true, it's true if B is true, and it's true if they're both true. Fine. And this is how the rules are going to look. So this is the equivalent. This is the math up here. What did I do? Okay. Had me nervous. I was like, is there some horrible bug? Probably there is. Anyway, this is how the rules are going to look. There's going to be parentheses, and then this line, and then sort of the conclusion down here, and the premises above, right? So we're saying, if you ask me to type an expression, and the environment, let's call it end. This is just Rust pattern matching, so end. And the expression is a variable, the name of which will be called x, then I can compute the type by running this steps on top. Like, I'm going to ask the environment to look up the variable x. You see that I put the question mark? That's because actually this, the way it's defined, can return a result. So this is the definition of that function. It's just a method defined in Rust on the environment. And it returns something which is fallible. What is fallible? Well, that's my cute nickname for anyhow result. So it just returns a thing that may succeed or not, right? And so question mark just says, well, if this returns okay, then the rule applies. If it returns error, the rule doesn't apply. But we track the error value for giving you better error messages later, because we're going to want to tell you why the type rule failed. And we would like to use this error message when we do so. And if that succeeds, then we know the type of x, and that becomes the final result, right? So this is one way to compute the type of an expression in the case that it's a variable. There might be other ways. There aren't in this case, but there could be. Okay. So let me show you that just to prove I'm not lying. How do I use my editor? Let's see. Where did I do this? So this is the actual project, e.g. main. I have no idea where the code is, so I just have to read it. But now you can kind of see what the main, I should show you this. Oops. So yeah, so this is a Rust program. I can run it. I don't even remember what arguments it takes. Let's see. No. Right. So I can use it to execute expressions. I wish this annoys me all the time. Okay. I can use it to do mistyped expressions, and then I'm going to get an error message, which looks pretty crazy. But actually, it's telling you exactly what's going on. I'll explain it in a second. But basically, it's saying, hey, I tried to compute the type of this expression in this environment, and I wasn't able to do so. Why? This is handy. Because this rule, there's a rule, so I'm jumping in here, a rule for typing additions, and it did not apply. It almost applied, but it didn't. And why didn't it? Well, because there was another rule that was for typing binary expressions. Don't ignore that for a second. Let's jump down. And eventually, I was supposed to compute the left and the right. They were supposed to be equal, but they weren't, so I got it false. So this is kind of telling you, I tried to prove it with the rules you had. I haven't shown you all these rules. I'm kind of jumping out of order, but that's okay. And where I hit dead ends, I'm going to propagate it back up so that you can see why these rules didn't apply. But ultimately, the rules didn't apply. This is not a valid program, right? And here now you can actually see the 10 minutes. Okay. Can actually see the real code. So type expert, just like I said, and it's a macro here, and here's some rules. Let's scroll down. Where was the rule I just gave? This is the rule for variables, right? And we have other rules, like the rule for lets, which I'm about to tell you about right now. So this is the rule for lets. It's a little more complicated. It's kind of interesting. What does it say? Well, when we're going to type an expression, it starts from this environment. If it's a let expression with a variable and an initializer and a body, then what are we going to do? We're going to recursively type the initializer. So we're going to compute what was the type of the initializer and store it in this variable var ty. And you'll note that this uses this right-hand arrow. So that's basically applying the judgment again. It's saying, let me type this expression. And remember I said it may have more than one possible type. So when you use that arrow, that's kind of saying, pick some type, right? It doesn't matter which one. If there's more than one, just take one of them, whichever one you like. And as long as it's valid for one of them. And then we're going to create a new environment, right? And so I'm going to call this function with program variable on the variable env, and I'm going to make a new variable called env. So here I'm leveraging Rust's ability to shadow. This is probably horrific if you're used to formal stuff, but it's very, very convenient because it basically lets us say for everything from this row down, I mean this modified environment, which has more variables than the original one, because I just brought the new variable into scope, right? And then I can, so when I do this last thing where I type the body, where I had let a equals b, or let a equals some expression, I'm going to type that other expression, then I'll use this modified environment. So I have the new variable in scope. So, and that'll give me the result. Okay, let me run that just for fun. So here's an example like this, right? If I say, let x is 22, so this works, of course, but what's happening? Here's the rule. So in this rule, the variable var is going to be x. The initializer is 22. And then the body is 44 plus x, right? So we're going to type the initializer, that is 22, and we're going to get back this U32. that's the type. Then we're going to make a new environment. Before we had an empty environment because there were no variables at all. So that's going to become, what is this crazy thing? No. That's going to become like basically just, saying, hey, we now have a variable called x that has type U32. And if you look at the definition of this function, all it does is insert something into the map. Very simple. And then we're going to retype this expression in this modified environment. Right? But now when we type 44 plus x, when we go to look up the type of x, we'll get that it's an integer. So typing binary operators, this is kind of interesting. It's actually a little different in the source code, but this is the basic idea. It's sort of simplified. I'm going to type the left and the right-hand side. They're both going to give me a type, lty and rty, and then I'm going to check if they're equal. So this is a little bit less elegant. If you were to write this mathematically in a more formal notation, you'd usually write it like this, where you just use the same t everywhere, and that implicitly means it must be the same type in all three places. But because of the shadowing and other things that Rust does, you have to write it like this, where you give two different names and then assert that they're equal, but it still works. Okay. So I've been doing demos throughout, but that's okay. What I'm going to do, how much time do I got left? Okay, a few more minutes, cool. I'm going to show you one other thing, which is, maybe you know about this and maybe you don't, but one of the things I really like is that all of this is just Rust code, right? And so what that means is, I can write a test, like test that 1 plus 2 as a tuple should not be addable to an integer. And then I can run this test, right? And it's just a Rust analyzer test, so it just works. Oh, hey, it passed, but maybe, let's suppose I want to modify the test now. So now the test is going to succeed, meaning this is well typed, but I've told it that I should assert, I had this handy utility function that says, when you give me back a result, it should be an error, right? So of course this is not going to pass now. This is sort of simulating the experience. Well, let me do a better way. Let's suppose I went in and modified my rules. I would start to get the, where did I have this if lty? Yeah, here. If I just take this if out, now I'm saying I can now type it. I don't actually care if it equals the type I expected it to equal. I'm not actually testing for that. So of course, when I run this, I'm going to get a test failure, right? So this lets me I also get a bunch of warnings, which is cool, but this is sort of the same way you develop any other code, right? You have your tests, you run your tests, you check that, oh, I made some changes to the type system. Does it still behave the way I expected it to on all my examples? Oh, good. And we also make use of this expect. I don't know if you've all seen expect, but it's a Rust analyzer supplied crate that lets you have kind of what was the result you expected. And so here you can see I'm saying, I actually expect this to fail, not just fail, but fail in this particular way, right? That the type did not equal the expected type. And then I can go in and tell the IDE using Rust Analyzer run. However I do that. No, how do I do it? Okay, well, it's not working for some reason. I think because I'm not in the right place, but there's a way to run it if this was not just a markdown, but also if this project was working, that would automatically update this with whatever the correct output is, right? Because this is a pain in the ass to type it in. But you can have Rust Analyzer fill it in for you. Super useful. Or you can even just do this. Cargo test dash update expect is one. Now, of course, I'm encoding this bug directly into my test, which I really shouldn't do. But you can see that it updated to the new output. So what this new output actually says, this leads me into my final point, I guess. It's still getting an error. Why is that? It's getting an error because I also wrote an interpreter, and the interpreter is now executing, right? Before the type, so if you look at what happens when you run a given test, it first, here we go. It first tries to check the program. If that check succeeds, it will actually run the program. So before it was failing here because the type check was failing. But now the type check is succeeding because I broke the type checker. And so it's running the program. But the program is getting an error because it doesn't know how to add tuples and integers, right? So why is that cool? That's cool because although I haven't written it yet, and I wanted to, I was hoping to demo it for you, but I didn't do it yet. What we can do is we can start applying fuzz testing and other techniques. Right? We can say, hey, the purpose of my type checker is to guarantee that my interpreter will never fail in this way. It should never be possible to type check a program and then have it try to add tuples and integers because that should fail the type check. So I can ask the fuzzer to go and try to show that that's true, generate random programs for me. And it's not just going to be like random strings, right? It actually is going to be generating random instances of my Rust programs, my Rust structure. So they're like well-formed programs. And we can see, will we ever find an example that causes the runtime to fail even though it passed the type check? And that doesn't give us, if we can't find an example, of course, we haven't proven that our type check is sound, but we've increased our confidence. And what my experience has been is that usually what I do is fuzz testing in Rust is like Niko says something that he thinks is true and then puts it on Zulip, and then people say, no, it's not. Look at this example program. And that's great. But it would be also nice if I didn't have to have people awake on Zulip. I could do it locally and then put it to the Zulip figure out the hard stuff. So that's sort of where we want to get to, I guess, is I want to be able to do the fuzz testing. I want to be able to do a few other nice things. I don't want to have this hack, whatever this is, I forgot. But, and we'd like to be able to, stepping back one step, when we use, there is a version of this that we're building out that models the actual Rust type checker in its almost full complexity. And so my goal is that we can actually run that on real Rust programs, and look for interesting cases like, hey, the real Rust compiler accepts this program, but the model says it shouldn't. Is that a bug? It's a bug somewhere, but where, I don't know. Possibly in the real Rust type checker, more likely, but maybe not, maybe in the model, and vice versa, right? We can look for discrepancies and kind of test and build up the model and make it more accurate. So that's all I got. Thank you for listening. I'm happy to have questions.
Wow, very cool to see academic work also being actually used in this way for Rust in the future, at least. Very nice. So are there any questions?
That's all very cute.
Thank you.
How does it scale up to real things like Rust with trait implementation, inference, and lifetimes and everything like that? How well does, when you really try to use it in anger, how does it stand up?
Well, let me see what I have here. I don't know how up to date it is because I usually work on a remote desktop, but this is the local. I mean, the short version is we're finding out. I think pretty well. It doesn't. Keep in mind that sort of intentionally, things like the trait system or type inference aren't part of the formality core, right? They're part of the rules we write, and that's because we want to check that Rust's inference rules work. While it does not yet implement the full system, it does have an implementation, for example, of coherence and the trait system. And let me see if I can find you a fun... Here's a little example where, get rid of that, where, okay, this is a little bit weird, but here's the base program that we're taking as input. We have a trait called iterator, a trait called mirror, which defines an associated type. We implement mirror for all types A with the associated type equal to A. We have a local type and a local trait, right? And then I'm generating sample programs based on that base thing with extra things. So if it's just that base code, it type checks correctly. But if it's just that base code and I have a second iterator that causes an overlap, then indeed I get an impls may overlap. So it's scaling up to a reasonably complete thing here. but I'm not yet doing the thing I was saying I want to do of like fuzzing it against Rust C and so forth. So I can't say how many fun dark corners we will discover. I will say one other thing. My goal is, one thing I didn't say so far is that formality core is like, what if you wrote Rust and you didn't care at all about performance? What if you cloned everywhere you could just for fun? You were like, I don't need to clone it, but I'm going to do it anyway. So I don't expect this to really scale to like hundreds of lines of code. I'm happy if it scales to tens. I think it actually does scale to hundreds, but that's not really my goal. Like, I just want small, usually a type system bug can be shown in like 4 lines of code. That's what I want to do. So it's absolutely prioritizing as clean and clear as possible over performance.
Another question.
Hello. I heard that Rust is either moving or has already moved to semantic lifetimes. So I was wondering, can the system describe those? How does it do it?
So oh, what's wrong? Oh, there we go. Wrong command. I've been playing with this, and I have this other programming language. It's a toy. It's for fun. But in that context, I was trying out mirror formality to get a feel for how well does it work if I want to. And in this one, this is like a really weird way to talk about this. But anyway, in this one, it does handle it's kind of a playground for what might the borrow checker look like if it worked that way. And I have modeled a lot of those things in this model and found that it scales out pretty well, and I was able to test stuff. We're now in the process of sort of taking this model, or at least I'm thinking about doing this, taking this model and porting it over to Rust, right? And implementing the borrow checker, Rust's borrow checker, kind of in this style, in a similar way. So the short answer is yes, it will scale to that, and we've kind of proven it out, but not on Rust. And I expect to do it on Rust next. Rust is a little more complicated, has other things to deal with. That was the whole point of doing it here, was to, even with a model, Rust is too complicated, but if we take a model of Rust and model that, we can do it, and then we can step our way there. You want to see syntax? Okay, let's look at some syntax. I don't even remember is the problem. This language is very different in its syntax, but let's find one example. I shouldn't have opened this module. Let's look for a test. Where are they? How do I make this work? -S. Yeah. Here's a test. Okay, here's a test showing in this crazy language. Like I said, this is a weird way to introduce it, but that's okay. Showing you have a class choice with a shared reference to self.pair. So it's using internal references within the struct too, which is, I think, is something we can do in Rust if we revamp our model. And I'm able to create a pair like this and share it around. So this is like, I guess, going to Jim's point, this is showing the system scaling up to kind of new languages and languages that do other kinds of interesting type checker ones. I want to show one that gets an error somewhere. Oh, here's a fun error. One thing I've noticed, it might be nice to trim these errors a little bit, because the only important part is sort of this last part here of why did this exactly fail. But what is this example doing? I don't know. These are too complicated. I can't find a nice simple one that looks easy to explain, but this is doing something bogus.
I might have just missed this in the talk, but you seem to have made something that helps you construct an AST using grammar rules, that helps you make inferences over it. There's like a bajillion frameworks that do this already. What is the reason to remake that in Rust?
Good question. That's actually a really good question, because initially I didn't want to do it in Rust. I built the whole thing in PLT Redux. It was beautiful. PLT Redux was a great system, but I had this problem. I want Rust contributors to use it. My goal is that we're going to have a model that is going to be, when you write an RFC that touches the type system, maybe not you, but somebody is going to take that idea and extend the model before we finalize it, right? Before we stabilize it, we will model it and test it and fuzz test it and play with it, and that's how the types team will come to understand it. But for that to work, turns out nobody wanted to learn Racket. They're used to Rust. They wanted to work in Rust. It makes sense. But also, what I found was many of those systems, at least the ones I played with, weren't designed for long-term engineering, right? Like Redux was explicitly designed to be a playground that you use also in the short term. Like you build a little example, you learn some stuff, and then you throw it away. And so trying to maintain that over time, it didn't have the type checking and so forth. I was like, why can't I just use Rust? Like I want to write a match and know that I have exhaustively covered all the cases, and I want to do all the things that Rust does well. So actually, I found the two blend together really well, that using Rust, the system feels playful, but it gives me the nice Rust type checking guarantees that I'm accustomed to and finds a lot of stupid bugs. I mean, we even saw it here, right? Like I commented out one line and all of a sudden I'm getting warnings about unused variables and stuff like that. So that kind of helped me already, before I even get to running my test, weed out most of the stupid bugs that I had to deal with. I can't say that I explored every single system, but the ones I tried, this was just a better experience for what I'm trying to do.
All right. I have also one question. You have this nice notation which came from mathematics, of course, from the programming language papers. Why did you choose to make it look like those inference rules in the papers?
As opposed to like just Rust code or something?
Because you want to appeal to the theoretical programming language strategies, or is it reduces it boilerplate?
There's a reason. I guess one, it's a good question. There's a reason that the papers use that notation, is sort of the short version. It's a really good notation once you get used to it for thinking about your type system and writing those rules down. It's very concise. And so what I found in formality, actually, I didn't show you all of this, but actually it's a bit of a hybrid, right? Like you kind of saw it when you wrote the program that first calls check program and then executes it. That was just regular Rust code. Or the environment, those methods, those were just regular Rust code. But then some of the stuff was in type rules. The actual rule of thumb that I've been following in mere formality is sort of, I actually use Rust syntax whenever I can. And it usually makes sense. For anything that's like purely deterministic, it makes a lot of sense. But when you get into trait matching and when you get into some of the more complicated type rules, there's a lot of sort of options. And in the Rust compiler, we've written a bunch of potentially correct code that like tries to decide which of those options to use in an efficient and thoughtful way. But mere formality just tries everything, right? It's just like, okay, you got 4 options. Let me just try them all and see if any of them work. And so that takes a lot of the load off of you, the person writing the rules, because you don't have to think about how you decide which rule to use. That's somebody else's problem. You just have to think about, if you took one of these rules, would it be correct? Right? Would it be correct to accept it in the case that these hypotheses match? And you can think about each rule one at a time, because it doesn't matter which rule you take. They should be correct no matter which one. So that sort of simplifies your mode, and I found it's just a really helpful construct. So I guess I use it because it's good. There's a reason everybody uses it. It makes sense.
Okay, so final question.
First of all, thank you so much for this talk. It was amazing. I really enjoyed it. I had a question. I remember hearing that the Rust language doesn't technically have a formal specification. Do you see this as part of moving in that direction as well in the future?
It's a good question, and I'm glad you enjoyed it. And yes, I do see this as part of moving in that direction. So we've got a couple of efforts going on that are sort of interrelated, and I think time will tell how they end up playing out. One is there's the spec working group that's actually kind of authoring a spec, starting from the Ferrocene work. Actually, Mara's here. Mara works on that. That's one effort, and that's going to produce, I think, something closer to what you would expect if you go to a traditional Rust language traditional language specification, right? And then you have sort of mere formality, and you also have Ralph Young's mini Rust, which is a different, sort of similar but different effort to formalize the unsafe code rules. And they're both basically written in Rust code, right? They're both executable, very precise definitions in some sense of different parts of Rust. I don't know exactly how they're going to end up relating. Maybe it's just that we'll check for consistency. I kind of like the idea that the sort of English language spec will not go into all the detail of saying exactly how the borrow checker works or exactly how the type checker works, but it'll say something like, there is a borrow checker and it guarantees this invariance. You know, your program doesn't reference memory like this, your program doesn't do that. And then we can sort of test, if maybe mere formality defines the borrow checker very precisely, we can test it against those invariants and say, can we actually find an example that violates those invariants and passes the type checker? That's a problem, right? That's a bug somewhere. Either the invariants are wrong or the mere formality is wrong. So I think that's a nice separation. That's what I'm interested, at least for the first draft, but maybe over time we'll find a different relationship is better. I don't know.
Okay. I don't think my mic is working. Okay, so thank you, Niko, for this fantastic
Thanks.
talk. Yeah.